Here, let's talk a little bit about some exceptions in bonding. Now, we've seen already that we really simplify the idea of bonding earlier with the concept of noble gas electron configuration and the necessity of atoms to try and attain noble gas electron configuration, or full shells of electrons. Now, as you probably have already realized, noble gas electron configuration and full shell of electrons, these two terms don't necessarily completely tie with each other. Now let's take a couple of examples, one in ionic and one covalent. Copper, for example, as a metal in the transition elements in the D block there. The electron configuration of copper is the same up to argon, which is why we have argon in a square bracket, and then 3d10 for S1. I don't really want to go into why it is that electron configuration. Let's just leave it as the fact that that is as it is. But when we consider copper 2, we tend to lose the 4s electron and a 3d electron. Now, copper 2+, of course, is quite a common sort of copper ion. Copper sulfate sits in the lab for many years as a blue solid or a blue solution and doesn't do anything at all. In other words, it's pretty stable. But notice that this isn't a noble gas electron configuration, nor does it have a full shell of electrons. So this is a good example of something that doesn't tie in with our simplistic ideas. Now we can go a little bit further. If, for example, we take copper 1. Now, copper 1 is another oxidation state of copper, and you'll notice the electron configuration is 3d10. Now, copper 1 does exist. I mean, you can have copper 1 oxide, for example, copper 1 carbonate, copper 1 iodide, and all of these are nice, relatively stable compounds, not necessarily any more or less stable than the copper 2. But notice that it does have a full shell of electrons, but it doesn't have noble gas electron configuration. So we can't just rely on very simplistic concepts in all cases. There are always going to be exceptions to the rules, and in fact, in some ways, one could say that the simplistic rule is the exception itself. Here's another one that we have come across a little bit before, boron trifluoride. Boron has 3 electrons in its outermost shell. It can form 3 covalent bonds, therefore, with fluorine, but that leaves a vacant orbital. It means it's not got a full shell of electrons, it hasn't got noble gas electron configuration, but it can react with ammonia, forming a dative covalent bond to gain noble gas, if you like, electron configuration. But BF3 does exist.